Welcome back to the next big session of computational thinking. In our conversational videos that we saw, the lectures that we had so far, you must have seen basically this bottom-up computing method is a very different kind of method from what we have seen so far. And how is it different? It's different because typically in all the algorithms or pseudocode that we wrote, the code remains fixed, right? We look at all the data, we do all the analysis, we write the code. Once the code is written, it's gold, it's fixed. And then you can keep giving it different data elements, it runs through the data elements and it gives you a result. That is how the code was structured earlier. Now, we are asking that, so that is why the normal algorithm or pseudocode method is what is called top-down method. Now we are asking, what if our code can keep changing? Nothing to prevent our code from keeping on changing. We can keep on rewriting the code, right? So what if we can basically change the code as we see data? So for first few data elements, the code might have been okay, but when a new data element comes, you find that this code is not looking good. So we change the code, right? So if your code can become dynamic, you can keep changing, then it becomes very hard to understand what is going on. That is one of the problems. So we need a very simple template which is then used to produce the code. If you don't have this template, if you allow any code to be added or subtracted from the given piece of program, then after some data comes in and goes out, your code is not going to be any more like what it was before, and you will never understand what is going on, right? There will be so many bugs in it, you will never be able to fix it. So as it is the program, analyzing it, you must have seen it's not that easy task. If you keep changing, then it becomes even more hard. So we want a simple template from which the code is constructed, so that you're not getting random pieces of code coming. It is filling some kind of bucket, right? If something is there, some structure is there inside which the code is getting filled, in which the code is getting filled. So it's easier to understand what is going on. And if for this kind of programming method, computing method, where there is a template into which you keep on filling things, and at the end of some amount of data, the template is completely filled out, you now have a piece of code, and then you can apply this code to new data elements. It's called bottom-up computing. Now, as we saw in the previous lectures, there are two kinds of problems that are suitable for bottom-up computing. The first kind of problem is what is called a classification problem. Okay. In the classification problem, the idea, the task is to label a data set that is coming in, the data element that is coming in, as something. Like for example, you want to label something as a car or as a tree or something like that if it's a picture, right? Or if it's handwriting, you want to basically identify a character. Is it A, B, C, is it a 1 or a 2 or a 0.5 or something? Or if you have a picture, you might say, is it a picture of a person, then you basically from the face you want to identify who the person is, maybe by looking at the nose, eyes and all this. Or you might have the data might actually be the symptoms the doctor has collected about a patient. Can I identify the disease by using looking at the symptoms? These are examples of classification. So you are classifying the handwriting into characters, or the faces into people, or names of people, or the symptoms into diseases and so on. Okay. The second kind of problem we have is what is called prediction. Okay. In prediction, what you do is you are given some data values and you are not given some data values. You want to find the not given data values from the given data values. Typically, for example, there are some observable values you can see of something going on, and there are some hidden things which you can't see. So can I guess what those hidden things are by looking at what is observed, right? I can't see the hidden thing. Can I guess what the hidden thing is by looking at the observed values? This is one way of doing prediction. Another way is, of course, I can't see the future. Of course, some people say they can see the future. I don't do it. So, can I predict what will happen in the future by using past values? So, one way is to use past values to find future values. Another way is to find hidden values from observable values. So, these are two ways to use prediction. So, examples are, for example, you can try to predict what the traffic will be at 10 o'clock tomorrow in one of the junctions in Chennai, for example. Or what will be the sales of this company next year. Or what is going to be the weather in Chennai next year, tomorrow, right? So these are all things which you can do, try and predict from the data. So I have past weather patterns for all the days of the year for the last 10, 20 years. I can use that to compute the weather for Chennai. Or similarly, sales also, I have various parameters. I can use that to figure it out. So we saw simple examples of classification, right? So we try to identify a student from the profile or from the marks or something like that, or the grades, right? Or we try to find a shopper. Who is the shopper? Is this Srivatsan? Is this Ahmed? Who is it? And all by looking at the buying behavior, right? We also try to predict the total marks given marks in two subjects. This is more like a predictive type. So we said basically given marks in physics, maths and chemistry, can we find physics, or physics and chemistry, can we find maths, something like that. Okay. So in this lecture we are not going to discuss classification, just going to take one more example of prediction, because in the previous lectures that we had, we kind of delved into it a little bit, not too much. Perhaps you benefit by seeing one more example in a little bit more detail through slides and so on. So we are going to actually go through one more example of prediction in more detail in this lecture. Okay. So what is the problem we are going to address? Problem is that of predicting train delay. Everybody has faced this problem, right? You go to the station, you're expecting the train to come at 10:30, and at 11 o'clock it has still not come, 11:30 it has still not come. You're fidgety, you're nervous, you need to reach someplace and so on. So all these issues, right? Planes also get delayed, trains get delayed. Trains get delayed for a very specific reason. Often the train is delayed because the trains prior to it in some stations are delayed, right? Because the trains share a track. So if the prior train is delayed, then basically it is still occupying the track. So unless it clears it, the train can't go. So that's why it's delayed. Or a station, for example, a train is sitting in a platform, and so unless the train goes from that platform, you cannot enter the platform. So that's why it may get delayed. So because there are shared platforms or shared tracks, therefore the trains get delayed, and tracks, the same track only enters the platform, right? The track enters the platform, so shared platforms in some sense already models shared tracks. So we shall only consider shared platforms in this lecture, right? And we'll ignore shared tracks, they're closely related, so we'll consider only shared platforms, right? And what is the problem that we are looking at? We are assuming that there are three trains, T1, T2 and T. We have information about T1, T2, and we also have information about T, right? We'll see, okay. T1 and T2, but what we know is that T1 and T2 arrive at a particular station S before T arrives. So T1 comes, then T2 comes, or T2 comes, then T1 comes, then T comes, right? That's how they come in the station S. Prior to the arrival of T, there is T1 and T2. So if T1 and T2 are delayed, there is a chance that T is also delayed. Okay, that is basically what it is. What we are provided with is a table whose entries are the delays of T1, T2 and T. Some examples of T1, T2 and T delays as recorded in the station S. That is what we have. Each column represents either T1 or T2 or T, and each row represents a day. Okay, here is an example of a table. So we have T1 delay, we have T2 delay, and we have T delay. So if you see this first row here, it says basically that T1 delay is 20, T2 delay is 25, and the T delay is 20. So it says basically that on some day, right? Some day last week, let's say last Monday, 20 minutes of day. This is in minutes, right? Each row is in minutes. 20 minutes of delay T1, 25 minutes T2, and then T was delayed by 20 minutes. Similarly, on Tuesday, T1 was delayed 10 minutes, T2 was delayed 50 minutes, and T was delayed 40 minutes, like that. Okay, so those are the rows. Now we are given some number of days, for previous days, and what we know for today. Today we are waiting for the train T, but we know that T1 and T2 are already delayed. How many minutes delay? We know that T1 is delayed by 75 minutes, and we know T2 is delayed by 40 minutes. Remember, T1 and T2 come before, right? Maybe even 1 hour before in station S compared to T, right? It's possible. So we want to know basically what is the delay of T going to be today. Can we use this delays of the previous days, right? 5 days that we have got, 5-day information. Can we use it to predict the delay of T today? This is the question we are asking, right? So we know basically that T1 and T2 are delayed by 70 and 5 and 40 minutes. We don't know T is delay, but we have the past days values, right? We have all these values for the past days. So can we do something? Now the usual way in prediction is to try and predict, find a numerical function that somehow computes the value of T delay from T1 delay and T2 delay. That is how we do the numerical computation. So the simplest way is do a weighted sum. Let us assume there are weights W1 and W2 that we can assign to the delays of trains T1 and T2. Let's say T1's delay is delta 1, T2's delay is delta 2. We assign weight W1 to T1, W2 to T2. So the delay of train T is going to be, let us say, W1, our estimation, our prediction, our guess of the delay of train T is W1 times delta 1 plus W2 times delta 2 But we are given for 5 days, we are given also the value of delta. So our objective, our problem now is to find the W1 and W2 such that W1 delta 1 plus W2 delta 2 for each row is as close to delta as possible. For each row, right? You have to look at all the rows. So each row we want to make W1 delta 1 plus W2 delta 2 as close to delta as possible. Really there are 5 rows, there are only 2 variables. Now we know that if there are only 2 rows, then we can solve it. 2 simultaneous equations, we can solve for W1 W2. But we have 5 rows, so it's what we might call an over-defined problem, right? So we have too many values, too many rows, too many numbers, right? So what we can do is we can try to make it as close to delta as possible for as many rows as possible, right? We can try that. Let us see how to do it, okay? Now we have to start somewhere. So it's a good way to start by saying that we don't know anything, so we can assume basically that both of them are equal, right? So we assume that both of them are equal weight. So they are 0.58 each, right? So we can assume that. So we'll assume that both of them have 0.58 each and then start. Now where do you start? Let us start with the first row, right? Let's start with the first row. So remember I was given the first row, I was given delay of T1 which was 20. I was given the delay of T2 which is 25 and the delay of T which is 20. What I have done is I have computed another delay. This delay is called the calculated delay, right? 22.5. And then I have found out another thing which is called the squared error function. I have not written squared just to save space, but it's a squared error function, and that squared error function is 6.25. Let's see how we have calculated this, right? So the calculated delay is, remember our weights are W1 is 0.5 and W2 is 0.5. So our calculated delay is apply a weight of 0.5 on 20, apply a weight of 0.5 on 25. So you get 0.5 into 20 plus 0.5 into 25. And so 0.5 into 20 is 10, 0.5 into 25 is 12.5, so 20 plus 10 plus 12.5 is 22.5. So the sum of those two gives me 22.5, and so that's how I calculated 22.5, right? That is the sum. Now this 22.5, you want to see what the error is. Now the actual delay which you got for that day is 20, but you calculated 22.5. So the error, the difference is 22.5 minus 20, and we have called the square of that the error. The reason we are squaring it is because we want to remove negative signs. We don't want to worry about negative and positive signs. And squaring gives you the impression of a distance, right? You remember that x square plus y square is equal to r square. X square plus y square is the distance. You know, kind of this way you calculate for x and y coordinates. You do x1 minus x2, y1 minus y2, square of them, and then add. That's how you get the distance, right? So we are, something like that is what we want to do. So that is why we are taking square. So 22.5 minus 20 is 2.5, and you square 2.5, you get 6.25, which is why the error is 6.25. All right. Now, strictly speaking, we could say that look, I calculated 22.5, which is higher than 20. So I must reduce 22.5 to 20. So I must reduce the weights a little bit. Then the error can be made 0. I can do that. But since I find the error is small, right? 6.25 is considered small. So I say, let's not bother. Let's go ahead. Okay, let's just go ahead. Let us try the second row, right? Now, second row basically had values 10 and 50. And again, I must do the following, right? I must calculate the delay. How do I calculate the delay? The weights were 0.5 and 0.5, remember. So I can apply 0.5 weight to 10, I get 5, 0.5 weight to 50, I get 25, 25 plus 5 is 30. So that's how we got the calculated delay is 30, right? But the actual delay is 40. So the difference is 30 minus 40 is minus 10, and I square that, I get 100. That's a high error. 100 is a high error. So I say I can't tolerate an error of 100 and all. So I want to reduce. Now where do I reduce? I could try to reduce the weight of T1, but this number is very small, so it doesn't make sense. So what I will do is I will only reduce T2 because that one has a higher number, right? So I will try and reduce T2. So let us say I reduce T2. How much do I reduce T2 by? Now see, the difference between this and this is 10, right? 40 minus 30 is 10. 30 minus 40 is minus 10. So I must somehow, I have basically calculated 30, the actual delay is 40. So I have underestimated. So if I have underestimated, I must somehow increase the calculated delay by a number which is 10. Now I must put a weight on T2 such that the increase is 10. How much weight should I put? Clearly the weight I must put is such that 10 by 50, right? So I want to get an increase of 10. 40 minus 30 is 10. I must get an increase of 10 by applying a weight on 50. So 10 by 50 is the weight I must increase. So if I add 0.2 to the weight W2, that is, if I make W2 equal to 0.7, then basically this 100 error should vanish. Okay, let us see whether that works, right? So what I did basically is I changed my weight to 0.5 now, and W2 I increased by 0.2 to 0.7, and then if I calculate the second row, the error vanishes. It's got to 0. Exactly how I wanted it to be, right? It's correct. But the problem is that the error of the first row now has become 56.25. Error of the first row is 56.25, right? Why did it become 56.25? Because the weight of W2 is now 0.7. So when I do the calculation, I do 0.7 to 25 plus 0.5 to 20, it is 27.5. And the error is 27.5 minus 20, which is 56.25. So the error of the first row has gone up. I could say this error is okay and just move ahead, but I'm not happy with 56.25. I want to control this 56.25 a little bit. So since I just increased weight of W2, let me see if I can tinker with W1 to get the error down. Okay. So let us reduce W, and so I want to reduce, how much should I reduce W1 by to make the error go away? Because we know the calculated delay is higher, right? Calculated delay is higher by 7.5. So I want to reduce the calculated delay by 7.5. And I have a number which is 20. So how do I get 7.5 from 20? So 7.5 divided by 20 is 0.375. So if I subtract from W1 0.375, then it should go away. So if I subtract from earlier value of W1 was 0.5, I am reducing 0.375 from it, so I get 0.125. So I can now compute the, clearly because that's what I did, error of first row has become 0, but now the second row has an error, right? Now the second row has become 14.0. But 14.06 is a small error. I think it's a small error. So we ignore it and we go ahead. Let us look at row 3 now. Okay. What are the weights now? The weights are W1 has been adjusted to 0.125 and W2 has been adjusted to 0.7. These are the new weights. So using these weights, I take row 3, right? Row 3, the delay is given are 50 and 15. I can calculate. How do I calculate? 50 into 0.125 plus 0.7 into 15, right? That gives me 16.75, right? That gives me 16.75. The error is 35 minus 16.75, or other actually, correctly if you do 16.75 minus 35 and then square it, so you get 333. Huge error, okay, huge error. So we don't like this, right? We don't like this 333. Clearly, when we did the increase, we increased the weight, we did some adjustment from W1, whatever we did, basically we reduced it, we reduced the weight of W1. Now this guy has got a huge W1, 50. And we made the weight of W1 0.125, very small, right? So that is why this thing has happened, right? So in some sense we want to go back. We are saying no, this was an overkill. We did too much of an adjustment to W1. Let us see whether I can upward adjust it. How much should I upward adjust it? Now the difference between 16.7 and 35 is basically 18.25. And if I divide it by 50, I get 0.26. So I should adjust it upward by 0.36. But if I add 0.36 to 0.125, I get 0.485, which is close to 0.5, where I started. It's pointless to go back, then I will just go back to 0.5 and I will start again. I don't want to go back and start again. So I'll say I will not take it all the way back to 0.5. I started with 0.5, I came down to 0.125. I don't want to go back to 0.5 again. Let me go somewhere in the middle. How much in the middle? I must also reduce the delay. So let us say I go to 0.4. There's a scientific way of getting to 0.4, but anyway, I'm getting as close to 0.5 as possible, but not get to 0.5, right? That's the idea. So let's say I put it at 0.4 and see what I get. So with the delay 0.4 and this thing, we now find basically that the delay, calculated delay becomes 30.5 and the error becomes 50.25. But now these things also have an error. You can calculate the error of these two lines. Fortunately, the error is not that high. This guy is 30, it's a little high, but it's not that high. In fact, actually, rather than the error now, I want to compute something else. I want to compute the average error. Okay, what is the average error? I have 3 errors, 30.25, 1 and 20.25. I can add up all 3 and divide it by 3. That is the average error. So 30 plus 20, 50 plus 1 is 51, divided by 3, 17. Average error is 17. That is pretty okay. Okay, so I am done with row 3. Now I want to go to row 4. Okay, so row 4, weights now, what are the weights? W1 is 0.4, W2 is 0.7, and I am now basically computing row 4. So let us do row 4, same way, 0.4 into 40 plus 0.7 to 80 is 72. Wow, 72 is damn close to 70, right? So the error is just 2 square is 4, very, very low, no problem. Okay, so I am just going to, and in fact actually not only has it done that, the average error has come down even more, because if I take the average of these 4 rows now, 30 plus 1 plus 20 by 4 is just 14. Okay, So it has become 14, average error has become 14. I am very happy. I now go to row 5. Okay. When I go to row 5, basically again I have given these delays 25 and 15, and now I want to calculate it with the same weights 0.4 and 0.7. I find that the calculated delay is 20.5. Lucky, I got lucky, right? 20.5 minus 20 is just 0.5, square it, I get 0.25, and not only is this value low, it actually brought the average even further down. It's now at 11. Okay, so I'm very happy with this weights. What are the weights? Weights are 0.4 and 0.7. So now I can say basically that I have a reasonably good confidence that the weights 0.4 and 0.7 work, because it's giving me low average error for the set. So I say basically that I'm going to predict that the prediction function is 0.4 into delta 1 plus 0.7 into delta 2. That is the prediction function. Okay, now what do I need to do? I'm given this new data set, which is 75 minutes of delay for T1 and 40 minutes of delay for T2, which is the data for today. This is today's data, right? Today's data. We got 75 minutes of delay for T1 and 40 minutes of delay for T2, and we are asked to find the delay for T. We don't know the delay for T for today, right? Because it's not yet happened. T is yet to come. We don't know. But I can calculate the delay using this prediction function. So I do that, and what do I get? 0.4 into 75 plus 0.7 into 40 gives me 58. And so what I'm going to do basically is I'm going to predict. I'm going to say the delay of train T today is 58 minutes. And you can say, hey, listen, if T1 was delayed 75 minutes, how can it be less than that? It can be, because T1 is in the past. T1 and T2 came to the station as before T. It could have been 1 or 2 hours before T, right? So that is in the past. That is why the data is available to you. You got those delays, and then from those delays you are trying to compute the delay, and this could be also a station long before the station which you are waiting. Some station S, not the station which you are waiting maybe also. Okay. But anyway, whatever it is, you know basically that the calculated delay of the train T when at S, at least you know, can be 58 minutes by using this method. So bottom up computing, as a summary, what is it? In a classification, what we try to do basically is that what we have seen, we didn't see it in this lecture, but we saw it in some of the previous lectures in this week. We try to make a tree-like structure, it's a decision tree. Each node of the decision tree, basically we try to figure out, based on the data set, data element that we have, we try to decide which branch to take of the tree. Okay. So one of the branches is chosen based on the data. And when you go down the branches of the tree, you hit the leaf finally. At the leaf is sitting a label which is assigned to the element. So you will say, you go down this branch and come to the leaf, you have hit the letter A. If you come down like this, you hit the letter B. You can do character recognition like that. Alright. Or if you come like this, you have that person, some person's name here, another person's name there, so you recognize the person by face or whatever. So leaf node contains a classification. Prediction, on the other hand, what we are trying to do basically is to make a numerical function that takes certain values and returns a value, right? So it basically is a linear numerical function. It need not be linear, but usually in most of these things we don't linear, right? Non-linear stuff is very hard to do, right? So linear numerical function that connects the value of the predicted value to the numerical value, the known value. From the known values, you are trying to find a predicted value. Obviously, one can combine classification prediction. One way of combining classification prediction is that the branch in the classification tree can be based on a prediction. Which means you can first compute an unknown value from a known value and use the cutoff on the unknown value to take a branch. You can first compute an unknown value and then say, if the unknown value is between 0 and 1, 0 and 10, go in the first branch. If it's between 10 and 20, take the second branch. 20 and 30, take the third branch. You can do like that. So prediction can be used as one step in the classification. This is one way it can be combined. The other way is, you can first make a decision tree, and in the leaf, instead of using a label, you can have a prediction function sitting there. You can have a tree, decision tree. You go down the decision tree using the data, and at the leaf, you use a prediction function to actually calculate a numerical. So that way you can combine both prediction and classification, and you get much more interesting kinds of bottom-up computing. Okay. So with that, we come to the end of all the content of this course. In the next lecture, what you will see basically is a summary of the concepts that we have introduced in the course. That will be the last presentation that you will have to watch. Thank you.